Hello, anatomy students, and welcome to the anatomy video series. Today, we're going to discuss the respiratory system video lesson 3, and we're going to cover gas laws, and we're going to talk a little bit about Boyles Law, which is what allows us to breathe here on planet Earth, and is just further evidence that we are, for lack of a better term, custom built to breathe here on good old Mother Earth. So let's go ahead and get started. All right, so let's get started with video lesson 3, and today we are going to be talking about gas laws. So let's get started with our first slide, understanding gases. To understand the mechanics involved in breathing, we first need to discuss some physics of gases called gas laws. All right, and there's one in particular that hopefully we will find that after we learn a little bit about it, you will see that we are custom, for lack of a better term, we are custom built to breathe here on planet Earth. The respiratory system depends on the medium of Earth's atmosphere to extract the oxygen necessary for life. So let's talk about our atmosphere. Our atmosphere is made up primarily of nitrogen gas. 78% of the air that you breathe in to your body is made up of nitrogen. So a while back, there was a tire company that was selling what they call, quote unquote, nitrogen inflation. And they were charging you extra to put nitrogen gas in your tires. They were taking advantage of people's lack of science and overall knowledge because just by pumping regular old air from the atmosphere into the tire, it was already 78% nitrogen. So that if they were doing 100% nitrogen, you're only paying for that additional 22% of the gas that goes into your tires. So see, a little bit of knowledge can save you money. So your atmosphere, the atmosphere we breathe in, 78% nitrogen, only 21% oxygen. You may know that in Earth's history, during the times, the Jurassic or maybe even the Triassic period, the atmosphere had a different consistency. There was more oxygen. This is what led insects to be much larger than they are today. Because of their type of breathing. But yeah, the air we breathe in is only 21% oxygen. That means the atmosphere is only 0.4% carbon dioxide. So when you hear people talk about the carbon dioxide levels in our atmosphere, it's less than 0.5% of all the gas in our atmosphere. So don't let their numbers scare you too much. When they're talking about the carbon dioxide, it's really, levels may be increasing and decreasing and whatnot, but we're really only dealing with less than 0.5% of the atmosphere. All other gases in the atmosphere will then make up that remaining fraction of a percentage. And then, of course, there's water vapor. The clouds are water vapor. And that will be different depending on where you are on planet Earth. Of course, the water vapor in the atmosphere over Brazil is going to have a lot more, a higher percentage than, say, the atmosphere over Death Valley, California. So it all kind of depends on where you are. There are many different units used to measure atmospheric pressure. All atmospheric pressures are usually given at sea level when you talk about averages. And of course, that is where the air meets the ocean. And since most of planet Earth is covered by ocean, that's a pretty fair assessment. So one of the units is pounds per square inch. So right now, If you were standing on the beach, you would be experiencing 14.7 pounds per square inch of air pushing in on you at all times. Another metric version is 760 millimeters of mercury, or you can change that into 29.9 inches of mercury equals 1 atmosphere. If you go below sea level, say which in most places you go below sea level, you're underwater. But there are a couple places in the world where you can actually stand on dry land and be under sea level. Those numbers will go up, and you will be a slightly higher, experiencing slightly higher than 1 atmosphere. And if you go up in altitude, in elevation, then you will experience a lower number. There will be less atmosphere pushing down on you. That's why when they climb to Mount Everest, they have to take oxygen with them. So at high altitudes, the atmospheric pressure is less. Descending to sea level, the atmospheric pressure becomes greater. Gases obey laws of physics called the gas laws. These laws apply equally to the gases of the atmosphere, the gas in our lungs, the gases dissolved in blood, the gases diffusing in and out of the cells in our body. All of these gases, regardless of where they are in our respiratory tract or in the stages of our respiratory system, they will all follow these gas laws. And the one gas law that in particular that we are going to focus on is called Boyles Law. Boyles Law applies to containers with flexible walls, such as our thoracic cage, also known as our rib cage. This is where your lungs and heart are kept. And as we talked about in the other lesson, we know that the lungs are enclosed in their own protective membrane, and then the lining of the chest cavity itself has its own protective membrane called the parietal pleura. And then, of course, the lungs are covered with a visceral pleura, which makes basically your chest is a closed container. There's only one opening, and that is your trachea. Boyles' law states that the volume and pressure are inversely related. Another way to say that is the volume of a closed container is inversely proportional to its pressure. What that simply means is when one changes, the other will change in the opposite direction. So if the volume of a closed container goes up, the pressure of the air inside that container will go down. And the inverse is when the volume decreases, then the pressure increases. That's what inversely proportional means. So again, Boyles' law states that the volume of a closed container is inversely proportional to its pressure. Gas will always move from a region of high pressure to a region of low pressure. Applying Boyles' law, if the volume inside the thoracic cavity increases, then the pressure will decrease, which is what I just said. Pulmonary ventilation. So pulmonary ventilation is simply, you have 3 parts to the act of breathing. The first is pulmonary ventilation, and then we have internal respiration and external respiration. And it technically in the correct order would be pulmonary ventilation, external respiration, and then internal respiration. And we will discuss the differences of those 3 over the course of the next few slides. Pulmonary ventilation is the movement of air between the atmosphere and the alveoli and consists of inhalation and exhalation. So pulmonary ventilation simply is getting air in your lungs and then pushing air back out. That's it. That's all pulmonary ventilation means. Ventilating, moving air. Ventilating or breathing is made possible by changes in the intrathoracic volume. So here's how we breathe, okay? This individual here, you see their diaphragm. It is bent up this way right here. It's the bottom of your thoracic cavity. When you breathe, you contract the muscles in your diaphragm, and when they get shorter, then the diaphragm flattens out. This is an increase. So now the volume of your thoracic cavity has now increased. And due to Boyles Law, the increase in volume means there's a decrease in pressure. Lucky for us, that pressure goes slightly below atmospheric pressure. And then the atmosphere, because of Boyles Law and gas laws, gases will always move to an area of lower pressure. Since the pressure inside our chest is now below what the pressure in the atmosphere is, that means the atmosphere then pushes the air into your chest so that it is equal to what the atmospheric pressure is. So if atmospheric pressure is about 760 millimeters mercury, when your diaphragm drops, you go down to an internal pressure of about 756 millimeters mercury, and you start to create a vacuum. And nature abhors a vacuum. So the atmosphere wants to have everything equal, so the air from the atmosphere rushes into your body so that the pressure is all equalized. And then now you have equalized the air pressure, or the atmosphere has equalized the air pressure inside your thoracic cavity. Your diaphragm is still contracted. And then when you go to exhale, you simply relax. Most of the time, you just relax the diaphragm. That causes the diaphragm to go up here. That is going to reduce the overall volume of your chest cavity. And when the volume goes down, the pressure goes up. And look here, it goes up above 760 degrees mercury, millimeters mercury. So that means, again, we've created a difference. Now the air pressure outside of your chest is lower than inside of your chest, and that wants to be at equilibrium. So that means the air leaves your body, and now the air pressure inside your chest is equal to atmospheric pressure. And that's how we breathe. Custom made to do that right here on planet Earth. So when you watch the news and we're talking about trying to find another planet for our species to live on, it's going to be very, very difficult, not only to find a planet, but to find a planet that's going to have an atmosphere very similar to ours. Not only does it need to have oxygen, but it better have at least close to 21%. We probably would be okay if it was a little higher than 21%, but it also needs to have an atmospheric pressure similar to what we have here on Earth. So even if it's 21% oxygen, but the atmospheric pressure the atmosphere's thinner, and let's say it's only 500 millimeters mercury, plenty of oxygen, but the air's so thin and the atmospheric pressure is so light that it would be very, very difficult for us to breathe. So it's going to be a monumental task to find another planet that is going to have a suitable atmosphere for us to survive. And then we have to get there, and that's another monumental task in itself, and that's for a different class. So let's move on. In contrast to ventilation, respiration is the exchange of gases. So we have, as I mentioned, they have three components to breathing. The first that we talked about, of course, is pulmonary ventilation, and that is simply getting air in and out. The next step is external respiration, and this is where gases in the lungs will exchange with the gas in the blood. So oxygen in the atmosphere will then leave the atmosphere and diffuse through the wall of the alveoli into the capillary beds, and will then dissolve into the blood. And then internal respiration is where the oxygen in the blood will then be pumped to the tissues all around the body, and that oxygen will then dissolve from the blood into the capillary beds of those tissues, and that's how we supply oxygen to all of our tissues. External respiration in the lungs is possible because of the implications of Boyles Law that we have already stated. And remember, Boyles Law says that the volume of a closed container is inversely proportional to its pressure. And so the volume of the thoracic cavity can be increased or decreased by the action of the diaphragm. And again, remember, when we take a breath, the diaphragm, that muscle that's at the bottom, is the boundary between our thoracic cavity and our abdominal cavity. That muscle, when it contracts, it flattens out, it lowers, goes lower in the body. That increases the volume, which decreases the pressure, and air rushes into our body. So everybody thinks that when we take a breath, we suck air into our bodies, when really all we do is we create a pressure gradient or a pressure difference, and the atmosphere takes care of the rest. It then pushes the air into our bodies, and that's all mostly controlled by the diaphragm. There is, when you take a big breath, there are some other muscles in the chest that can help increase the volume. You can elevate the ribs a little bit with some of the intercostals and your sternocleidomastoid muscle and so forth. But for the most part, the bulk of the heavy lifting is done by the diaphragm. By changing the volume of the thoracic cavity, the pressure in the lungs will also change. Changes in air pressure result in the movement of air, again, due to Boyles Law. Contraction of due to the gas laws. Contraction of the diaphragm and external intercostal rib muscles. Those are the muscles that are in between the ribs. Increase the size of the thorax. This decreases the interpleural pressure. That's the pressure inside that pleural membrane that's going to be inside the lungs, so air can flow in from the atmosphere. This is called inhalation or inspiration. Relaxation of the diaphragm. Breathing out is usually a passive process. You simply relax the diaphragm, and the air will rush out of your body. With or without contraction of the intercostals, decreases the size of the thorax. So that is a decrease in the volume, which is an increase in pressure, and that results in the air being exhaled. Certain thoracic muscles participate in inhalation. Others aid exhalation. The diaphragm is the primary muscle of respiration. All others are accessory muscles. So again, that simply means that the diaphragm is going to do most of the work. It's the prime mover of air in and out of your body. The recruitment of accessory muscles greatly depends on whether the respiration movements are quiet, which is normal breathing, also known as eupnea, E-U-P-N-E-A, eupnea. Gosh, I wonder if me spelling it out is important. Hint, hint, wink, wink, nudge, nudge, know what I mean? And then you have forced, or sometimes called labored breathing, where you are actively trying to, if you exercise and build up an oxygen debt, and you are really working on breathing, or if you are my age and you're trying to blow out birthday candles that someone has evilly placed all the years on the cake, you're going to need a big breath. So then that will be a more forced type of breathing. Okay. So again, you're going to see, and you look in this diagram, you see we're going to float back and forth around that magical atmospheric pressure of 760 millimeters mercury. You see, it's not a big change to breathe in or breathe out. So when we go to inhale, we will increase the volume of our chest. That brings the pressure inside the lungs down below atmospheric pressure. The atmosphere then wants to make things equal, so the air will rush in, and you will have an atmospheric pressure that will be nearly equal. You'll have an interpleural pressure inside your lungs nearly equal to the atmosphere. And then when we exhale, the diaphragm relaxes and it goes in an upwards fashion, which is going to decrease the volume, and that's going to increase the pressure over atmospheric pressure of 760 millimeters mercury, and you will breathe out. And I think that is going to do it for today. All right, that should do it for video lesson 3. If we are on remote, you will be directed back to Schoology to go answer your exit slip. If we're not on remote and you're watching this because you're quarantined, there'll be no exit slip, but this is here again to make sure that you can keep up with us here in class. So hopefully that spells out everything for you. And if you have any questions, just shoot me an email. Thanks for watching. We'll talk to you later.